Hello, my name is Kyle Shorey, and this is lab report number 6. Alright, so I'll start off by introducing the lab, going through the procedure, then the model, the errors, and then the what if. So, to start off, the purpose of this lab is to explore Faraday's law of electromagnetic induction by dropping a magnet through an aluminum foil and measuring the fall time. As the magnet moves, it changes the magnetic flux, which causes eddy currents to occur, and those currents actually oppose the magnetic fields, or they create opposing magnetic fields to the force of gravity, slowing the magnet's fall. Overall, it reinforces the principles of conservation of energy, as electrical energy is temporarily stored and dissipated. Preview of the results. From the experiment, 0.974 seconds was the amount of time it took to go through the tube, and then the simulated time, 1.04 seconds. The equations we're using, Biot-Savart law, the magnetic flux equation, and Faraday's and Lenz's law equation, and then also some kinematic equations. So here's a diagram, essentially, of what we're doing. You can see there's a lot of arrows here, but essentially the main point is that the magnetic force will be opposing the gravitational force as the magnet continues moving down the tube. Our procedure to start off, obviously gather the materials, then figure out which side is north and south, and then you drop the magnet through the tube with the north side up. You make the measurements of the time, and then as well as measurements on the aluminum foil to get the radius and the length and all of the important stuff from there. Then you repeat dropping it like 5 times, get the average from there, and that is how we got our experimental time. Then we created a glow strip model using the measurements of the tube to figure out what the ideal time should be. And then the assumptions we made while running the experiment were that a bar magnet can be treated as a magnetic dipole. The only forces present are magnetic and gravitational, and then there's negligible air resistance. So our system is a bar magnet, the surroundings are the tinfoil, tube, and everything else. So, experiment. Here are our 5 trials. You can see, once again, our average was 0.974 seconds. And then we imported the data that we got into the code directly. So here you can see that. The computational model. So starting off, you need the dipole B function, which essentially uses the Biot-Savart equation, just written in code form. It takes mu, which we gave it as an initial condition to start off. And then we have the calculating the deflux, which is essentially just taking the integral of B, the magnetic field, right? So you can see what we got as our answer here, and then how that translates into code form. And then, yeah, the rest of this initial conditions down here, you can see the mu mag that we gave it initially. And then in the top right, we have the magnetic forces that we're calculating. And then the net force with gravity is as a player in that, and then also the velocity and position update formulas for our graph. And so this was our graph. I know it's kind of hard to see, but there's a little bit of blue down there, and as it went down the tube, you could see the blue and red as it was going down. Here's our graph. Uh, this initial portion right here, or the initial portion up to about 0.1 seconds, you can see is where velocity or speed was increasing. So that means that the force of gravity was bigger than the magnetic force. And then through this time, you can see the change is pretty much negligible. So they're equal, which means that the velocity was constant. Uh, and then and that the magnetic force was equal to the gravitational force. And then at the end here again, you can see gravitational force is greater again once it leaves the tube. So this constant area is where we see that the magnet is within the tube. Some potential errors and improvements that we can make to this lab. The friction on the side of the tube as the magnet fell through. The axes might have been measured incorrectly, and then air resistance could affect it as well, and then potentially human error not timing the fall correctly. So what if, and what does it mean? So what if the resistivity of the conductor were reduced as close to as possible to zero? How would the dynamics of the falling magnet change? So lowering the resistivity would lower the resistance, which would increase the induced current, which means the magnetic forces opposing gravity would be stronger and we'd see a slower descent. If holes or slots were cut into the tubes, this would affect the ring currents because there would be less current rings, which would cause the magnetic force to decrease and the magnet would fall faster. But yeah, that's pretty much it. Thanks for watching.